As I mentioned before, if we want g of n to be equal to h of n, then the denominator here should be equal to 1. And one example that fulfills this condition is a sine window. So the sine window is a window given by this equation here, and we have this shape here in the plot of the sine window. As an example, if we use n equals to 512, we have a system delay given by 2 times capital N minus 1, so we have 1023 samples as the delay, and we see that it comes from the delay matrices. There's one block of capital N and the blocking delay of n minus 1, and then we have the system delay. In the frequency domain, we see that this sine window has a better attenuation outside of the passband than compared to a simple sink. There are many advantages using the MDCT. So we have improved frequency response, so higher stop band attenuation. We have easy to design filter banks with many subbands, for instance using n equals to 1024 for audio coding applications. We have efficient implementation using sparse matrices and a fast DCT, and it's very important when we use a large number of subbands as we use in audio coding. And here we can see some examples of the filter impulse responses using 1024 bands, and we see, for example, component H7 and component H15. So here is H7 and H15 using a sine window, and here we have the frequency response, so of the 7th band and of the 5th band, and we see that they are indeed better filters.